Today we will be looking at how to compute Pearson R correlation coefficient as well as Spearman's rule in R. So first let's look at Pearson's R. So for this we will first need data, and as you all know R has some inbuilt data sets. So if you want to get like a list of data sets that are available in R, you can use the library function, and in that you can use help equals data sets. So if you run this, you will get a list of data sets here. So these are the names of the data set, which you can use to call the data set. And here we will be going with the women data set because it's the most easiest one and least confusing. So it's just two variables, basically the height and weight for women are listed. So let's use this data set. First, I'll create a data frame to just look at how this looks. So here you can create a data frame, and the you can check what it was called. It's just called women. So yeah, you're right. R automatically gives you this inbuilt data sets that you can choose if you just start typing. So yeah, once you see, you will be able to view it if you click here. So here you can see the average weight for the height is mentioned. Now let's see if this data meets the assumptions for Pearson R, because Pearson R is a parametric test. It has several assumptions which need to be tested before we compute the correlation coefficient. If any of these assumptions are violated, we cannot move forward with computing the Pearson R coefficient. Then we will have to look for alternatives. So first assumption is that they have to be continuous. So here height and weight is supposed to be continuous. So you don't really have a test to see that. You can just conceptually understand whether your variables are continuous or not. So here height and weight are usually considered continuous. Next is that they have to be related pairs. So related pairs as in for each row, you need entry for both variables. So here so this is the weight for this height. So these are related pairs. So in each row of observation, you should have entry for both the variables. Then you can say it's related pairs. Next assumption is that they have to be linearly related. So linearly related. So basically, Pearson R measures the linear relationship between two variables. And before computing it, it makes sense to first visually check whether there is a linear relationship. By linear relationship, we mean that if you visually check the data, you can make out there, like you could draw a line through the data, and the data points would be closer to that line or would be increasing in a linear fashion. So you can test this visually. If you draw a plot, so in R, you can draw a plot with plot function. So here we can just plot the height and weight. So women, height, and weight. So if you plot this, you will see here that this is linearly increasing. Weight is increasing linearly with height. You can clearly draw a straight line through these plot points. So it means that they are linearly related. So this assumption is met. Next assumption is that there is it's the assumption of homoscedasticity. Basically, it's also called homogeneity of variance. So what this assumption says is that your value of each variable should have equal variance at each level of the other variable. Now it's difficult to understand this theoretically, and some of the sources I referred to, they had entirely skipped this, but it was mentioned in some other sources. So I guess it's better to just check this once. So you can check this visually again. If you see a cone shape forming when you plot both of your variables, if you see a cone shape forming, it means that this assumption is validated. So to test this, if you see here again, there is like no cone shape forming. but I remember seeing one data set which had a cone shape. So I'll just quickly make that data set. Okay. So here, there is one data set orange. If we plot, if you want to check this data set, you can see it's the circumference and age for the orange trees. So if we check this visually with the plot, here I remember seeing the cone shape, orange, age, circumference. So if you plot this, here it's showing a cone shape. So this is supposed to violate this assumption of homogeneity of variance, but some sources entirely skip this step. So yeah, I'm not very sure how strictly this is followed, but in some of the sources, this was checked. And there is one more very important assumption, that is the data has to be normally distributed. So the fifth assumption is that your normally distributed data. And this is supposed to be for both the variables. Both variables should follow normal distribution. And you can check this again visually with help of QQ-plot. So QQ-plot, there are two lines of code for QQ-plot. Okay, so you can do this with QQ-norm. So you just mention height and run this. You will see the individual points and then you plot the line. So the line is supposed to show how the normal distribution looks. And the closer the points are to this line, it means that your data follows a normal distribution. So here we see that our points here are very close to this line, which means our women's height variable is normally distributed. You have to check this again for the other variable, which is weight. So the same lines of code, QQ norm. Weight. QQ line. I don't know why this is coming. Okay, yeah, gone. Women weight. Okay, so if you run both these lines of code, you will get the QQ plot for weight. And again, these values are close to this line, so it's normally distributed. Even if these points were slightly further away from the line, we would still consider it normal distribution. Anything which is not very weird, like these lines shouldn't be here and here, like too far away. Even if it's slightly further away from this line, we would still consider it normal distribution. Okay, so because this data meets all the assumption, we can now move further with the computing the Pearson R correlation coefficient. So the code for computing that is very simple. It's just one line of code. So here you mentioned weight. You mentioned method. If you don't mention method is supposed to mean what kind of coefficient you want. If you don't mention it, by default, you get Pearson, but always better to keep mentioning it. So you have that practice. So yeah, here we have mentioned for test function, we mentioned the two variables for which we want to compute the correlation coefficient. Here I mentioned height and weight, and method is Pearson. So the correlation coefficient we get here is 0.99, which is very strong positive correlation. And this is almost 1, so perfect correlation. And it is highly significant. So it's almost a perfect correlation between height and weight. So yeah, so far we have seen how to compute the Pearson R correlation coefficient. Now, what if your data doesn't match, doesn't fulfill these assumptions? Like even if one assumption is violated, you cannot move further with Pearson R. So the other alternative, which is commonly used, is the Spearman's rho. Spearman's rho is a non-parametric alternative for Pearson R. basically, if any of these assumptions are not fulfilled or not met, you can move ahead and calculate Spearman's rho coefficient. And usually Spearman's rho is computed for ordinal level data. So your any data, for example, your rank or grade in school, it can be considered ordinal. So for measuring a Spearman rank correlation coefficient, let's create a vector. So let's create grades in school. Okay. So for this, let's take 1 to 10. So this would create a vector. So here basically these are first to 10th grade in a school. And this is one of our variables. This is ordinal level data. The next vector I want to create is marks. So here I'll just quickly mention the marks 14, 6, 20, 18, 19, 10, 6. Do we have 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So this is 10. So in each we have 10. Now for this, we can use Spearman's correlation coefficient. So again, it's the same line of code. Here, you again have to mention the grade. You can directly, because it's not a data frame, you can directly mention grade. And in method, this time you will mention Spearman. Okay, so if you run this for 1 second, I didn't run this line. What? There is an error. One. Okay, where is this error? Expected in marks. I'm not sure why I'm getting this error. Didn't we supposed to put a comma? What? Oh, okay. I'm so sorry. I didn't put the C, right? So sorry. You are supposed to put the C to create the vector. I didn't put the C, which is why it was giving me the error that it was not expecting it. So generally, if you want to know what the C does, you can just put a question mark before C. So R will tell you what C is for. So C combines all the values into a vector or a list. So for C, this is how you write the number. So it is separated by a comma. So I didn't put C, which is why I was getting the error. So yeah, so now we have the vectors ready, and now we can use this for test. Okay, so this error is must have same length. Usually you will get this error because data frames don't always have the same length. So, okay, let's count how many variables we have. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I don't know why, how initially I thought it was 10. Anyways, so now this should work. Okay, let's see. Okay, what another error? Few times. All right. So usually when you have the same number repeated, you get this warning message that it cannot compute exact p-value with ties. That usually means you have some number which is repeated. So let's just remove 1/6 and check what we get now. We can use some other variables, other number which has not been used, so 7. Now, even though we get this warning message here because there was one repeated number, it doesn't, I honestly don't know if it does a lot of harm. I'm yet to look into that, but just to avoid this warning message for now, let's not repeat a number. If you repeat a number in your data set, if there are numbers repeated for a variable, usually this warning message is shown. So to avoid this warning message, let's again try it. Okay, so now because there is nothing repeated, we don't have that warning message. So it becomes easier to move forward with interpretation. So here we see it's a weak negative correlation, which is not significant. So there is no significant relationship between our variables here, which is the grades and marks. So this whole vectors that we created, there is no significant relationship between them. Although although the correlation coefficient is weak negative, still because it's not significant, we report it as there is no significant correlation between these variables. And if you have such repeated values in your variables, which is usually the case, you can still compute it, but you will get this warning message. And honestly, right now, I'm not very sure what to do with the warning message, but this is a warning that you get. But we have removed the warning by not repeating the variable. And it's important to look more into what exactly the warning means. But right now, we are just looking at how to simply compute it in R. So yes, this is how you do it. These are the codes that you need to run. These are very simple one line of codes. And this file will also be uploaded if you want to run it yourself. And yeah, also there are many different correlation coefficients that one can compute depending on the kind of data. So because right now we don't have a lot of time, so I'm just showing these two. But some other time we can also look at all the different kinds of correlation coefficient out there and choosing the best